Okay, for number 27, we're going to have combustion reactions, but this is one we did in lab, methane, just in methane. You could skip at number 27. Number 28A this is single replacement. So skip that. B is double replacement, do that. C is double replacement. And so B and C were, we don't have to worry about. 29A, carbon is burned in air. This one, you know, carbon is solid carbon plus air would be O2 gas. This one we could form different products. For example, carbon monoxide gas and or carbon dioxide gas. So if you have a choice, we'll just go with complete, you know, complete combustion of carbon. Complete combustion of carbon will yield CO2, the higher the charge. So this is just carbon solid plus O2 gas yields carbon dioxide gas. That's as much as you can burn it. You can't burn it to carbon trioxide. So we leave it there. So this would be an element plus element combination reaction. We talked about, this is the same situation that happened with copper yesterday. We talked about it. Sodium metal and aqueous potassium chloride, that's single replacement there.
So are we not,
We're not doing that on this test. So B is not, 29B is not going to be on your test. It'll be on the next test. So you can expect more double replacement style reactions. Focus on double replacement and, did I say acid base? Double replacement and acid base and element plus element single replacement. So, I didn't finish it, but we're going to have element plus element. Yields compound. We're going to have a compound, it's just a reverse reaction. Compound decomposes into elements. So it'd be element plus element. The one way, both are redox reactions. So that was the redox. Then we have the metathesis, which we're going to just focus on the double replacement style metathesis. The whole then we're going to have acid base. For the acid base, we're just doing the redox. Not acid base, the Bronsted. The Bronsted method, acid base.
is that the one that you showed us with the 7 steps? That's not going to be on the test?
It's not really 7. I mean, probably. You don't do them, you do them all at once kind of thing. So you don't have to separate them into 7 individual steps. You just do them all at one time. .30, we're going to have to skip that because we haven't finished redox yet. So 30, what are the chemical properties of HNO3? And then this, of course, I might not make this a bonus. It might be just write the solubility rules, you know. Yeah, like all the rules. All the rules. If that's still a struggle, just do what I recommended, which is to write them down right before the test, and then right when you get the test, write them down. You know, that way you don't have to get them in your longer-term memory. That's only a short-term fix. You want to get them into your longer-term memory, but at least you don't want to lose points for that. So all the solubility rules. all nitrates are soluble. All group 1s are soluble. I'd first look at group 1. Hydrogen's group 1. Group 1 and ammonium are all soluble. Done. It's soluble. But nitrates, all nitrates are soluble too. We're done.
So that would be one chemical property.
That would be a physical property. Chemical property is what does it react with? What does HNO3 react with? React with bases. What bases would it react with? And then, is that it? Only acid base? Is that it? Is there anything else? You got to tell me. Yeah, acid base is one type of reaction. How many other types of reactions are there? Are there infinite? If there are infinite number, then I guess you can't tell me, but there aren't. They're a limited number. And so the others would be metathesis and redox. Metathesis, nothing happens with HNO3 pretty much. Not much happens, you know, with nitrate. But some stuff happens with H+. H+ like certain anions. And those anions could be termed substitute. So we're going to look at that in more detail later. Actually, tomorrow. Tomorrow I'm not going to use the entire lab period. Tomorrow we're going to look at some more chemical reactions. But today I want to just review. So what questions do you have from homework, from lecture, from this practice? Uh-huh. 26. Well, I was asking you what a formula. A formula is a atom ratio or mole ratio, not a mass ratio. You have the mass ratio there. And so the way we do this one is we have 82.7% carbon and 17.3% hydrogen. Should I write it hydrogen as H or H2? H. What we do, the first step is we assume 100 grams. If I have 100 grams, how many grams of carbon do I have? 100 grams total. I'd have 82.7 grams of carbon and 17.3 grams of hydrogen. This is a mass ratio, but we don't want a mass ratio, we want a mole ratio. So is it possible to go from grams to moles? Yeah, we need what? The molar mass. And so what we're going to do is we're going to go from grams to moles by doing this. On average, a mole of carbon is 12.01 grams. A mole of hydrogen is 1.01, but in this case what I'm going to do is I'm going to use the other one, which is 1.008 grams of hydrogen per mole. Hydrogen. This is the 4 sig fig since I'm just working with single atoms. If I'm doing H or H2, I'm going to use 1.008 for H and 1.016 for H2. And so I can get the mole ratio next. Let's get the mole ratio. 82.7. 82.7 divided by 12.01, 6.859. I'm going to go with at least four digits for this. 6.885. Moles. Maybe I'll go with 5 since this one's 9 moles of carbon. 17.3 divided by 1.08. 17.16. 2 moles of hydrogen. it's the mole ratio. What we want is the mole ratio, except we want it in terms of simple whole numbers. To get this in terms of simple whole numbers, we're going to divide by the smallest. And so, well, formula is mole ratio, so we'll just write this out as mole ratio. We'll have carbon 6.8859, hydrogen 17.162. To get these into simple whole numbers, we'll divide by the smallest, 6.8859, 6.8859. So what does that equal? Well, carbon's going to be 1.00. We're only allowed 3 sig figs, so just do 1.00 sub 0. Hydrogen, 17.162 divided by 6.8859. 2.490. All right, so I have a couple of things I could do here. I could round the hydrogen. If I were to round the hydrogen, I get 1 carbon, and what should I do? Should I round it up or should I round it down? Well, according to the rules, I should round this down. So this would be CH2. But you look at that rounding, if I round that, that's going to lead to a pretty big round off error, right? Pretty big round off error. It's like this. Remember, we were looking at this. If it's 100% 6, the mass is 6. If it's 100% 7, the mass is 7. If it's 50% 6 and 50% 7, then the mass is 6.5. Right? That's 50%. But let's say I got it at 49. And so it comes out to 6.49. Should I go ahead and round that to 6? 6.49 is close enough to 6? Just round it down. Would you feel comfortable with that? I think you'd feel comfortable. Let's say, you know, if you're buying something, if they round it down, it would be kind of nice. You know, the price is $2.49. I'll just round it down to $2, you know, rather than $2.49. Right? But if you're selling something, then maybe it's not so nice. You round it up, say to $3. This one is kind of a big round off. So what we do when we see something like that, when it comes out to a half, you know, we don't want to round it up or we don't want to round it down. Or if it comes out to a third or 2/3. If it comes out to a third or 2/3, we multiply by 3. If it comes out to a half, we multiply by 2. So what I'm going to do is I'm going to times 2 this rather than round it. And so this is going to give me carbon 2.000 and then hydrogen. If I double this, it's going to give me 5.980. Okay, now would you feel more comfortable rounding this to a 6? I'd feel a lot more comfortable, so I get C2H6. Now rather than round that.
For hydrogen, why did you divide the mass of carbon for the molecular formula?
Because I wanted to get it in simple ratios. Like, what's the ratio of hydrogen to oxygen? Hydrogen 2, oxygen 1. Well, let's say it wasn't like this. Let's say I had something like this. Hydrogen 6, oxygen would be 3. But I don't like to call water H6O3. Let's say I have 3 water molecules. What I'm going to do is I'm going to divide it by 3. to bring it down to simplest whole numbers. To bring it down to simplest whole numbers, this is going to come out to H2O. And so if I'm having weird numbers like this, the thing we always do is divide it by the smallest. This is one of the steps in the method. Why do I do it? It's because it's one of the steps of the method. So that's why you should do it. Are you asking me this? Are you asking me why am I doing it, or are you asking me, are you asking me, it's a step of the method, but why am I doing it, or you're not really sure? Is that a step of the method, or? Yeah, then just memorize it. This is the next step. After you get the mole ratio like this, the next step is to divide it by the smallest. You always do this. We always do this. The reason why we do it is to get it into the smallest whole numbers. That's the reason. So what's going to happen is when you do the moles, you're always going to get weird numbers. So let's say we analyzed water, and what we ended up with water is something like this: O3.28, H6.56. We get weird numbers because this is the mole ratio. And so it depends on how many grams of water we analyzed, but this is the mole ratio we got, but that's not the formula. The empirical formula is the simplest mole ratio, not whatever mole ratio we got, depending on how many grams of water we analyzed. And so the next step is to take this weird mole ratio, make it simpler by dividing it by the smallest number to get us to here. The reason why we get these moles is because it depends on how many grams we sent out for analysis. They're just going to tell us how many moles there were. And do you think you carefully measure out 1 mole and send that out? No. If you measured out 1 mole and sent that out, then it would work, of the compound.
How would the C2H6 equal 58U in the mass?
Okay. Well, unless I made a mistake. It's possible I could have made a mistake here, but if we look at the mass of this unit here, 2 carbons would be 2 times 1201, which is going to be 2402. And then 6 hydrogens would be 6 times 101, and that would be 606. And so when we combine these masses, I'm going to get 30.08 U here, 30.08 U. And so when I look at 30.08 U, then that's the mass of the empirical unit. But if I look at the mass of this, it's at 58 U. And so there's a problem here because the mass of the molecule has to be some integral multiple of this. And so the integral multiple of this was, unless there's a pretty big experimental error, it could be double this size, or it could be triple this size. And so it doesn't quite match because the next one would be double this size, which would be C4H12. If we double this, then we maintain the same ratio of carbon to hydrogen. C4H12 is the same ratio, carbon to hydrogen, but what we do is we'll double the mass, which should come out to 60.16. And so 58, either the 58U is wrong or there's something else wrong because it's off. Can you see that? And so either the molecular mass is way off or something else is wrong. This particular problem here. And so if this is 60.16, then it's off. We might be able to attribute it. The actual molecule weighs 58U, so this would be the closest here, unless I did something wrong over here. So what we do is we just double check these particular. We just double check these particular ones. And
It's hydrogen 5.6. That's 9 times 2 is 4.98.
yeah, oh sorry. That's what it would be. I was just going to check the numbers here. And so it is off. This would be 4.98, which we would round to 5. And so let's see if that fixes it. That means this is a 5. That means this would be a 5.05, which would give this a 29.07. So 29.07, then C4H10 would be 58.14. So the mistake was here. I made the mistake here. And so it was quite a bit off from what you would expect. So anyway, this is the empirical unit. The molecular unit weighs twice as much. So it's either going to be 2 times, 3 times, 4 times as much. So it has to be an integral, integer multiple of this. This is better, 58, because it's only 2 sig figs there. So 58.14, we could attribute it to round-off error or experimental error. But something like a 58 versus a 60, we have to attribute to some other type of error. Either an error in the molar mass or error here. Okay, so I was going to check the original problem, but it's not necessary. That was my mistake. The original problem is from your book. Okay, were there other questions? Acetic acid and calcium carbonate. Did anybody get that one? Acetic acid is, what's the formula for acetic acid? Good. Calcium carbonate? What's the acetic acid? Is it soluble or insoluble? Soluble. Calcium carbonate, is it soluble or insoluble? Not soluble. This is a solid, it's not soluble. Acetic acid would be aqueous. What does this form? Hydrogen carbonate. What's the formula for hydrogen carbonate? H2CO3. H2CO3 goes by another name. What is it? Carbonic acid. What do you know about carbonic acid? It's not stable. And decomposes into what? H2O liquid and CO2 state? Yes. Okay, so that's one product. What's the other product here? Okay. 2 of these. This is called calcium acetate. So it's calcium with acetate ion. Calcium acetate, is it soluble? Yeah, acetates, nitrates, acetates, chlorides, they're all soluble. So is there any driving force for this? Stronger acid to weaker acid. So let's consult the chart first and see if that's the case. Do you see acetic acid? Where's acetic acid?
Oh, that CH.
Yeah, CH3COOH. Is it stronger than carbonic acid? Yes. So what we can say is we're going from stronger acid to weaker acid. Acetic acid would be stronger acid, the weaker acid would be carbonic acid. That's a driving force. Is there anything else that drives this? What were the three driving gas formations? Stronger acid, weaker acid, and gas formation. Two driving forces. There's no precipitation. The three driving forces for metathesis: precipitation, stronger acid, weaker acid, and gas formation. So we have two of the three. All we need is how many? One. All right. Is it balanced? It's not balanced. How can we balance this one? Yeah, we need two hydrogens. That will give us two hydrogen ions here. Two acetates, one calcium, and then carbonate, one carbonate goes to one carbonate. This is balanced here. So balanced by ion is easier. So it's balanced now with the two here. This is the CE. What is the IE?
So when we're writing out the equation, the acid and carbonic acid, does that like cancel out or is that still there? Like, are we focusing on the water?
Well,
Or are we still focusing on that?
no, it's still there. What's still there is CO2. Did you know CO2 is not an acid in the traditional sense. The traditional sense is CO2 doesn't have hydrogen ion to give. But did you know CO2 is considered an acid? CO2 is considered a Lewis acid. Lewis acid has a little broader definition. And so this is actually stronger to weaker acid. The weaker acid is CO2. CO2 is the weaker acid. So we're going from acetic acid to weaker acid, CO2. Water is just present. Or you could go stronger acid to weaker acid, carbonic acid. So I'm just going to go to weaker acid here. This drives it. This is driving it, and then the carbonic acid decomposes. Carbonic acid decomposes here, making a gas, which further drives it. So one, we drive it by making the weaker acid. The weaker acid doesn't last very long. It decomposes, makes a gas, and the gas helps with the reaction along. It just so happens that the gas is also an acid, but the gas is going to bubble out of the solution. There are some gases that are acidic, some gases that are basic. Like oxygen gas is neutral. It's neither an acid or a base. Ammonia gas is what we call basic. CO2 gas is acidic. There's something, where people get too much CO2 or something, and they have a condition called acidosis. Have you heard of that? When we exhale, we're exhaling acid, CO2. It's maintaining our blood pH. If you don't exhale enough CO2, you can get into trouble. Your blood pH can go down. Anyway, let's go. Or hyperventilation. Ionic equations next. Let's take care of that since we're out of time, or we're running out of time. Acetic acid, strong acid. It's one of the 7 strong acids. I don't see it here. Strong acid? No. Strong base? No. Soluble salt? No. So what do we do? Just leave it alone. Nothing. Do nothing. Calcium carbonate, strong acid? No. Strong base? No. Soluble salt? No. Therefore, what do we do? Nothing. We leave it alone. H2O liquid, strong acid? No. Strong base? No. Soluble salt? No. Leave it alone. CO2 gas. Strong acid? No. Strong base? No. Soluble salt? No. So leave that alone. Calcium acetate. Strong acid? No. Strong base? No. Soluble salt? Yes. Acetates are all soluble. Therefore, we split it apart into what? Calcium ions and acetate ions. For every calcium ion, we need 2 acetate ions. So, are there any spectators here with the NIE? Do you see any spectators?
Everything except calcium and acetate ions.
Well, does acetic acid appear both on the left and the right? Do you see acetic acid on the right? No, I see acetate. Acetate and acetic acid are 2 different things. Acetic acid is an acid, acetate's actually a base. Acetate's a base. They're 2 different things. The acetic acid on the left is acetate on the right, that's base. So that changed, the acetic acid reacted. Calcium carbonate, do you see it on the left? Yes. Do I see it on the right? No. Calcium carbonate reacted. There are no spectators here, everything reacted. And so that means the IE and the NIE are the same thing. No spectators. Spectators are, it would appear on the left and the right, the same thing. So if I had an acetic acid on the left and an acetic acid on the right, I can cancel them out. Cancel it out. The spectators are like this, you know. This is what I do, like, you just have the same thing on the left and the right, like nitrate. The typical spectator would be nitrate. Nitrate on the left, nitrate on the right. They cancel each other out. That's what a spectator is.
So you would write nitrate yields and then the nitrate.
No. No. Let's do this one here. Barium nitrate and ammonium sulfate. We don't have much time, so I'm going to just write this out. We just have a minute. This is going to yield barium sulfate. Barium sulfate is a precipitate and ammonium nitrate. Ammonium nitrate doesn't precipitate. Balance this will need 2 ammonium nitrates. So the driving force for this is precipitation. Barium nitrate is a strong acid. No. Strong base? No. Soluble salt? Yes. All nitrate salts are soluble. So this barium 2 plus 2 nitrate. Ammonium sulfate. Strong acid? No. Strong base? No. Soluble salt? Yes. All ammonium salts are soluble. So 2 ammoniums for every sulfate. We've got to make sure we get the charges right. Charges are very important in chemistry. Barium sulfate, it's an insoluble salt. Leave it alone. Ammonium nitrate, that's a soluble salt, so split it up. 2 ammoniums, 2 nitrates. Make sure we get the charges in there. Do the bariums react? Yes. I have barium on the left, I don't have barium on the right, I have barium sulfate on the right. But that's not the same thing. Is barium ion the same thing as barium sulfate? No. I have nitrates on the left. 2 nitrates on the left. What do I have on the right? I have 2 nitrates. Exactly the same thing. It didn't change.
So that would be switched.
That's what we call a spectator. Ammonium, how about ammonium? Same thing, ammonium is a spectator. And so the net ionic is just going to be barium ions, like the sulfate ions, to form barium sulfate. This is why we call this metathesis. Metathesis is barium ions react with the sulfate ions. Metathesis are favorable ion combinations. This is why I don't call it double replacement, because if you look at this, does this look like a double replacement reaction to you? This is the reaction that happens. Double replacement is just a simple pattern for just figuring out what pairs of ions might like to combine. So that's spectator. Well, if you have more questions tomorrow, we can go through those.